Hello, I welcome you all to this another interesting screencast. We are going to be solving this engineering mechanics problem. And the problem reads, determine the moment of inertia of the area about the x-axis as well as the y-axis. This problem is coming from the engineering mechanics statics textbook, 13th edition by R.C. Benam. Right. So let's briefly discuss what moment of inertia is. Moment of inertia of an area, also called area moment of inertia, and sometimes it's also called second moment of area. This is a geometric property of a shape, such as a cross section of a beam, that describes how the area of that particular given shape is distributed around an axis or a chosen axis of interest. And the units that are used for this particular property is units of length to the power 4. Units of length, so this could be for SI units, millimeters to the power 4, meters to the power 4, and if it is imperial units, we are talking of feet to the power 4, inches to the power 4. And the main uses of moment of inertia, if I was to give an example in one discipline, which is structural engineering, we use it for calculating the deflections of beams, buckling loads of columns, and so on and so forth. And let me describe it quickly mathematically. If I had a very small area here, let's call this as our dA, and then we have a distance to this small area from the y-axis, which is x, and then another distance from the x-axis, which is y, and another distance from the center there, or which is r. So if we are to describe mathematically moment of inertia about the x-axis, is ix is equal to integral of y squared, which is squared the distance, since we are saying this is the second moment of area. We're taking moment here about an axis of an area twice. So like moment of inertia about the x-axis is ix is equal to integral of y squared dA, and moment of inertia about the y-axis, we have integral of x squared dA, and we also have what is called polar moment of inertia. This is about the z-axis or the zero pole z-axis, which is just equal to integral of r squared dA, which is also equal to just ix plus iy, since r squared is equal to x squared plus x squared plus y squared. I did a video, okay, where I explained further and gave an example of deflections of beams, where moment of inertia is applied and why it matters. So I'll check out the link at the end of this video so that you watch that video if you are interested to check that particular example. Right, so let's dive into the problem. So here we have this particular shape that is being governed by, or area that is being governed by this equation, y squared is equal to 1 minus 0.5x, and we want to start with finding the moment of inertia about the x-axis. Before we do so, we need to define, we get a differential strip, then later on label it, and after I've done so, then we start doing the work. So if we are taking moment of inertia about the x-axis, like I said in my previous video, we need to take a strip, a differential strip that is parallel to that axis of interest. Okay, so we want to take moment of inertia about the x-axis. I'll take a strip like so, because this makes the work easier. All right, that is just the reason that is about it. It makes the work easier, and we want work to be easier always, right? So let's take a strip of thickness dy, and it is cutting the curve at this point, which is This point here is just x comma y. We have this height here, which is just equal to y. Okay, is that so? What else do we have? We have the length of this small strip, which is x. We have the centroid location there. For this small strip, what is this location? This location is just half of x. This is the centroid location for this small strip. Okay, so this is x squared is equal to x divided by 2. Great. And then we can define our dA. Our dA is equal to x dy. Alright, this is more area. You have the length of x, thickness of dy. Great. So having said so, we have moment of inertia Ix equal to integral of y squared dA. We know what dA is. So y squared, our dA we said is just x dy. And the equation that is governing that curve is just y squared is equal to 1 minus 0.5x. And writing it in terms of x, this gives us x is equal to 1 minus x is equal to 2 minus 2 minus 2y squared. Okay, so replace this value here. We are going to replace this here, and if we did so, then we are going to have Ix is equal to integral. We are integrating with respect to y, therefore integration constants will be from -1 to 1, and then we have y squared, and then we replace the x with 2 minus 2y squared dy, and then Ix eventually is equal to, we expand this becomes a 2y squared minus 2y to the power 4 dy. Great. So there we go. Let's move on to some new space. Therefore our Ix is going to be equal to, we rest integrate that. Integrating that, this is going to be equal to 2y to the power 3 divided by 3 minus 2y to the power 5 divided by 5. Evaluating this from -1 to 1. And if we are to work out this, it's going to give us the following expression. We have a 2, just a 2 divided by 3 minus 2 divided by 5, then minus what do we have? We have minus 2 divided by 3 minus, and then minus 2 divided by 5. This eventually gives us, let's grab our calculator. We have 2 divided by 3 minus 2 divided by 5, then minus 2 divided by 3, then minus brackets minus 2 divided by 5. Okay, let me redo it, sorry. 2 divided by 3 minus 2 divided by 5, then minus, we have minus 2 divided by 3, then minus in brackets again minus 2 divided by 5. Okay, there we go. So we have a 0.5333 what are the units? Meters to the power 4. Great. So this is about it. We found the first part. So what we need to do now, we go to the second part, which is finding moment of inertia about the y-axis. So what do we do? we need to cut this, get a differential strip parallel to the axis of interest. This is one reason we do this again, is just to make the work easier. We always want easy steps. I mean, we have to make life easy. We want the easy part, right? Easy but accurate, right? Great. So that is going to be our dx, as the thickness is dx. Great. And then we have these heights. Then it is cutting the x-axis. I mean, it's cutting the curve. This point here, it is x comma minus y. This point here, it is x minus comma y. Therefore, this height here is y. This height here also is just y as well. Okay, it will be y also. Of course, it is going to be negative, but it is still y. Okay, so the whole length is 2y. And then we have this from the position from in the x direction, the location of this in the x direction is just x. Of course, the centroid of this is just here. Okay, this is the centroid along the x-axis, which is just x. And if you look at the first problem, moment of inertia about the x-axis, that was about the centroidal axis. So this answer we found, moment of inertia about the x-axis, is moment about the centroidal axis. Okay, so this time around we are finding moment of inertia about the y-axis. Okay, the y-axis in this case is not a centroidal axis. And then what is our dA here? Our dA therefore here is going to be equal to 2y. Okay, that's the whole length times dx. Great. So then we have iy, which is equal to integral of x squared dA. Okay, and therefore iy is equal to x squared dA is just a 2y dx. Then we know that our y squared is equal to 1 minus 0.5x, and our y is just going to be equal to root of 1 minus 0.5x. So replacing this y, we need to replace this y here. Great. If we did so, then we have iy is equal to integral along the x-axis. The integration constants are from 0 to 2. Then we have x squared, then root of x squared by 2. There is a 2 there. So let's factor out the 2. Okay, let's factor out the 2. Let me write this neatly. So this is equal to 2 integral from 0 to 2, and then we have x squared, then the y is just 1 minus 0.5x dx. Great. So there we are. Let's move on to the new space. So therefore our iy is going to be equal to, so when you look at this one here, this integral, we have the root. So one of the ways we can solve this is by substitution. We can say let u be equal to 1 minus 0.5 x, and therefore we know that our x in this particular case is going to be equal to, our x will be equal to 2u, right? 2u, no, not 2u, sorry, just 2 minus 2u. Okay, not so. Okay, yeah, so we can do this, and then we know that our du dx is just going to be equal to minus 0.5. So we can work out this easily. And when we work out that, we'll find that IY is equal to 2.4381 meters to the power 4. Great. So we have all the answers. So we have Ix, which is just equal to 0.5333 meters to the power 4. And we have moment about the y-axis, which is just a 2.4381 meters to the power 4. Of course, we have a higher moment of inertia about the y-axis, and it makes sense even when we look at the distribution of area from the y-axis. Check out the link if you want to check out that example I talked about on one of the applications of moment of inertia on the deflection of beams. Thank you for listening. I hope the video was helpful. If it was, give me a thumbs up, like my video, continue subscribing. Bye bye, and see you in my next screencast.